Now, Alvaro from talking about ToroDB.
Okay, thank you. Thank you very much. I think I can. May I skip the micro altogether? Oh, no. Okay, it's okay.
The font of the room is going to be hard.
Yeah. Okay. Fine enough. Just take it before Alexander.
Yeah, just come back.
Okay. Just.
Free hand. Thank you.
Okay. By the way, how do you want to raffle the shirts?
We'll collect names after.
Okay. Okay. There's the 3 TourDB T-shirts. They look like this. Although it will look better on you. There are 3 sizes: M, L, and XL. So, well, hope that will fit you. Okay. So, thank you very much for having me here. I really want to thank Frank for this opportunity. I'm not living in the US. I'm Spanish and I live in Spain. So it was just the matter that I was spending here some days and I got the opportunity to speak to you. Hope that this is going to be interesting. So what I want to talk about is something called ToroDB. How many of you know what it's Toro? In Spanish, not in Japanese. All right? Some of you? Yeah, it means bull, right? So that's our logo, right? The T-shirt again. It's not the Wall Street one. It's ours. Okay. And what is TourDB? So I'm gonna speak about it. So, but just basically, very simple. It's a new database. So how many of you here use databases? Whatever kind of databases. Okay. The rest of you, where do you store data?
Memory.
Memory? Okay. How do you persist data? Flat files. Okay. Good for you. All right. So this is a new database, and it's new in many senses. Not only from the age perspective, it's also new because it brings together the NoSQL and the relational world. So it's both a SQL and NoSQL database. And surprise, surprise, it's written in Java. So more than focusing on the user side of this database, you know, with the Java drivers or whatever, I'm going to focus on the development side. So if you would like to write Java code, if you would like to contribute code, because by the way, this is all open source, you're in the right place today. So let's get it started. First things first, a little bit about myself. My name is Alvaro, well, it's really Alvaro, if you can pronounce that. It's not that hard. I worked for a company called 8K Data. I'll buy you a beer for the first one who guesses what is the name of the company, what it means. It's related to databases. It's a little bit technical, but, well, you get the chance. And we mainly do research and development in databases. In other words, we find it fun to come up with crazy ideas about databases, and some of them we take them and try to build something out of them. TourDB is, of course, one of those. We are also Java developers. We do a lot of things with Java and also Postgres, which is our favorite relational database, just after TourDB, of course. As I was saying, we're the Java developers. We belong to Java specialists, and we go to JCrete, the hottest Java conference, literally. It's in Crete, in the Greek island. That's why it's very hot, because it's also in August. So, well, you get the idea. If you want to find me, I'm on LinkedIn, Twitter. By the way, our own Twitter is @NoSQL. Guess why? Okay, so let's get started. If you talk to database developers, which maybe you're not, if you're Java developers, but if you talk to your peers, which are developing the database, right? They all want a certain set of characteristics from the database of features. Like they want, of course, great functionality, because after all, database, that's what it is. It is a building block for creating applications, right? So if your database just give you a couple of functionalities, a couple of features, how do you develop an application with it? You'll end up doing everything in your application, and you probably will do it wrong. So just factoring all that work and letting the database or that tool you're relying on do that for you. So you want a lot of databases, a lot of functionality, a lot of features from your database. You mostly always want some kind of ACID consistency or an equivalent level of consistency, because again, otherwise, if you don't have this, you're gonna end up doing all that work on your application, and you'll probably get it wrong. Not saying you're a bad programmer, of course not, but it happens, right? And of course you want reliability. You don't want your database to lose data. Probably not. Maybe some cases, but usually not. And last but not least, I'm pretty sure you want most of the time SQL. Well, there's of course NoSQL, and NoSQL started as meaning not SQL. Then it meant something like not yet SQL. Now it means yes, we want SQL, but we can't, more or less. So yeah, most people want SQL because it's the lingua franca in terms of databases, and it's been here for a long time. It's very advanced. It is a language decoupled from the actual way of getting the data out of the database, and it's the market. People want SQL, right? So you want all this. But then, NoSQL came, and there is more requirements. Now people want NoSQL, like for example MongoDB. People want schema-less, and people want high scalability. Everybody wants to scale to the size of Google. Not everybody is Google, but everybody wants to scale that size. So we have tons of requirements, and unfortunately, these two sets of requirements are a little bit disjoint, right? So the first set of requirements, these ones, may match more or less the traditional relational databases. And these ones, to be schema-less, to be able to scale like Google, are more tied to NoSQL types of databases. So what do? You pick one, you pick the other. Well, fear no more. There's now TourDB, which basically brings you both of the sets of features in the same place, in the same software, in the same product. So think of it as a combination of a relational database like PostgreSQL and NoSQL database like MongoDB, all in the same place. And we're going to see how it is possible. But before that, let's try a demo. It will probably break, as you always know, but I'll take the risk. So, how many of you, okay, first of all, can you read the font? Is it okay?
Yeah.
Okay. How many of you have used MongoDB here? Okay, a few of you. So this is MongoDB, right? So for those of you who haven't used MongoDB, you type Mongo, this opens a cell, then you connect to a database, have set up a database called TourDB, right? And now you can issue commands to the MongoDB shell. So those commands are something like db dot, let's say, javasig dot insert, and then I can insert a given document. A document is a let's put it very simply, let's say a JSON document, okay? So I'm gonna craft a JSON document, A1, B2, and then I'm not really original with this, I suck a lot, but let's say, something, it's already used. Something like that. And it writes the result. So it basically means I have persisted this document durably into the database. And now I can query that document later with the find command, and it finds the document. There's some extra object ID over there, which is basically an internal field that it's created by MongoDB, right? So this is basically how more or less MongoDB works. Now, just for the sake of this demo, let's do something. Let's look for the MongoDB process, right? And well, there's a ton of stuff here, but to be honest, if we really look at those, and we try to, there's not going to be enough room here to check. Well, okay, it doesn't matter. If we query for those processes where there's a MongoDB process, let's pipe that a little bit. There's some Java stuff there. It's pretty long stuff. And then there's the grep command. This basically means that there's no MongoDB server running. Indeed, it's not even installed on my computer, MongoDB. So, what was happening here? Because after all, I was running against MongoDB, right? And data was there. If I use TourDB again, and yeah, data's there. I can still insert more stuff, and data will be there, but there's no MongoDB. So this is what TourDB is. TourDB is running and is impersonating MongoDB. It's a database that speaks the MongoDB protocol natively. So whatever you can do with MongoDB, at least theoretically, you can do with TourDB as well. Since it speaks the MongoDB protocol from a wire perspective, you can insert, you can query, you can update, you can do anything with MongoDB drivers, MongoDB tools, no change. It will behave as a MongoDB. Now, the cool part is the data. Where is it stored? Flat files? Definitely not. Data is being stored in Postgres. So now, this data that we have inserted is inserted in Postgres. And what we're going to see also is that data is not inserted as a blob. Or it's not inserted using a type which Postgres has, which is called JSOND, which allows you to store JSON data. No. There's a process by which data is transformed in a relational form. Pure tables. And it's stored as a set of relational tables. So let's get into that. So the demo kind of worked. And this is the non-Wall Street logo bull. Basically, to sum up TourDB, it's a document-oriented JSON NoSQL database. So it behaves as a NoSQL database, right? And exposes the MongoDB interface, as I mentioned before. It is open source. It is under the AGPL license, the Alvaro GPL version 3, and it's written in Java, completely written in Java. And of course, what is more important is that we have both the MongoDB compatibility and the Postgres layer, or the relational database layer, below. So the first question is, how do we map this unstructured data to relational data, to a relational way of mapping data? So just with a quick example, because I want to focus more on the Java topics, but just for you to understand how this works, take this simple example. Well, I'm not able to point a lot. But anyway, so take this example, and the first thing that we do is split the document in such a way that there will be no nested levels. So we split the document into parts, which we call document parts, not very originally, or subdocuments, such that they contain a single level of hierarchy. In this case, I would take name, data, and nested, which will belong to the same level. Then A and B, in the first row, that will be another level. Then J and deeper, that will also be another level. And finally, again, A and B. So we'll take this document, split in 4 pieces, more or less something like this, right? Name, data, and nested, A and B, J and deeper, and also A and B. Yeah?
One quick question. Do you only store JSON documents, or what kind of documents can you store there?
Okay. So the question is whether we store JSON documents or other documents. So far, we store anything that comes from the MongoDB protocol, and those are, let's say, JSON documents. They are not JSON, they're something else called BSON, but basically that's like JSON, right? So we store that. Now, internally, we use an abstraction layer, which I will talk about a little bit later, which is called KTB document, which abstracts us away from the concrete representation of an structured hierarchical document. So we can store basically anything which is hierarchical and structured, based on key values.
XML comes to mind, yeah?
Sorry?
XML comes to mind?
Well, XML could be transformed in such a way, but XML brings more, theoretically, it is a superset of what you can represent with JSON. But I believe it could be used to store XML if you develop this interface. Okay.
Thank you.
Sure. So we split the document into these 4 pieces, and now we have these brackets, which are placeholders. those do not need to store information per se, so we remove them. So for the first subdocument, we will only need to store the name TourDB. The second one will require A and B, and the third one we only need to store the J, the 42 value. Now that we have these parts, we match them to a relational table. So for instance, to store the A and B, we basically require a table with a column named A and a column named B, the first one being an integer, and the second one be the text, for example. If such a table doesn't exist, we will dynamically create this table with this exactly set of, with this definition, right? A number, B text. If it exists, there's nothing else to do. So first of all, TourDB will create dynamically tables to match your data, your incoming data. You don't need to predefine your data. Even though you were using a relational database, you don't need to define a schema prior to using it. Okay, so this is how it looks like in tables, more or less. Remember that object ID that is called in MongoDB the underscore ID? That's why it's showing up here. There's also some internal fields that we use called the DID and the index. DID stands for document ID. And the rest, you can see, it's just the data that we have, right? One thing to notice here is that there's one table that we are reusing here. That on table T1, there's entries for 2 subdocuments. This is interesting because, as we shall see later, just by reusing the table definition, we are saving a lot of metadata repetition, which happens in JSON collections. JSON collections allow you to vary the schema, to have different keys, different values in different documents. But at the end of the day, if you look at a collection with millions of documents, there's not so many different documents, because otherwise, how could you query that later? So documents end up having, you can have several, let's say, different versions or different types, but at the end of the day, that's a limited number. However, you're repeating all the time the name, the age, the surname. So there's a lot of people using MongoDB that just for this use one single letter key names, because it takes a lot of disk space. They are repeated all the time. We don't do that because they're factored in the table definition. Now, if you look at these tables, it's impossible to refactor back together the document. You need to link it somehow. So there's an extra table called structures. And this table basically holds the schema of that document, the structure of the document. This containtional data, it's just a way of expressing that, in this case, the root level of the data, it's stored on table number 3. If we go back to table number 3, this is effectively the root level, the one on top. Then it says that there's a nested field called data, and which is represented in table number 1, and then table number 1 with index set to null, that small star means null. It's represented, it contains the A and B, A42, B, hello world, and so forth. So basically these are kind of the pointers. And finally, we're using the relational theory here, and we're using a relation. So it turns out that what I was referring to before as the types of the documents, that they are repeated a lot, this is for us the structure. So the structure of the documents, this entry that you see here on the top, it's what gets repeated a lot when documents share the same structure and different data. So rather than having one entry per document for the structure table, we'll have one entry per different structure, and then a relation which is called root, where we link each document with the structure that they have. So that's the way we have to avoid schema repetition, structure repetition, and this saves a lot of disk space. Together with the meta information from the structure table and all the tables definitions that TourDB creates automatically, we're able to figure out which tables to look for when you do any query from the interface, the database interface. If you think a little bit farther, this picture basically depicts how NoSQL databases store data. But because basically you can have different types of data and one document will be stored next to the other without any order. It's a little bit of a chaos, but it's meant by NoSQL to be that way, right? Because you can store anything So the only way of storing anything is just to put one document after the other one, regardless of which type or shape or form they have. Whereas the way we store the information looks a little bit more like this, because we are classifying data based on the type that the data has, and we're storing them separately. Which means that whenever you need to do some kind of queries that favor this type of pattern, for example, aggregated queries, analytic types of queries, you get a lot of performance benefit. We'll see that later with benchmarks. But just imagine, if I give you this and I ask you, can you please sum up and compute the average and standard deviation of the yellow pieces? You basically need to scan everything. And this is exactly what happens with NoSQL databases. They continuously do database scans for analytic type of queries. Whereas in TourDB, you'll just go and say, oh, they're over there. So you look at that table or tables and scan those and resolve the query. Okay, so what this brings you, aside from data normalization and saving disk space, compared to other databases, or NoSQL databases like MongoDB. First of all, native SQL. Any of you here using Windows 3.11? No? Okay, then why you stick to SQL 92? Because most people who say SQL, they do join, group by, where, limit, offset. By the way, offset's not in standard, but it doesn't matter, right? And that's it. Well, that's SQL 92. SQL is much more advanced than that. It's extremely advanced. If you look, for example, at Postgres, there's an amazing array of features that you can do with Postgres. You can do recursive queries. How many of you did know that? You can do recursive queries with SQL. 1, 2, 3, 4. Okay, that's good. You can do window functions. You can do custom operators. You can do really, really cool stuff. So don't get stuck with SQL in the era of Windows 3.11. So for the same reason, SQL is such a powerful language, it's a shame not to have it on NoSQL. So the good news here is that while we are exposing a MongoDB interface, and you can interact with TourDB, with the MongoDB interface, both for writing and also for reading, so you can do the queries, as you've seen, in the MongoDB API, nobody prevents you, indeed we encourage you to go to the database directly and talk SQL, at least for queries, because it's such a powerful language. So just go and do SQL. So now you have both. You can insert data as MongoDB and then query data as SQL. This also allows you the possibility to mix and match both relational and non-relational workloads on your same set of systems, right? Let's imagine, which is not uncommon, that in your company where you work, there's only this database or this set of databases, or typically relational databases, which are the ones who are more still commonplace in the market. However, you want to operate as a NoSQL store, or your developers or your colleagues want to use MongoDB API because it's cooler, right? For whatever the reason, doesn't matter. However, it's a problem to introduce new databases in the stack. You need new servers typically, even if you're in the cloud. You need probably train people, you need certifications, you need backup policies, security policies. And so, what if you could just say, okay, you want NoSQL? You have NoSQL on your same database. You don't need to change anything. Your environment can remain. The backup system that we have can also work as is. There's nothing else to change. And at the same time, you want to keep on your traditional applications running exactly the same way. Well, the good news is that you can have both in the same database. And even if you have one application that is using one part of the database as a relational application and another application which is running TourDB and this is creating tables automatically, and in another part of the database, could be separated schemas, for instance, you can then join them later. You can use SQL joins to merge the data together. We don't prevent you from doing that. Again, we encourage you to do that. More advantages. I'm going to go a little bit more quicker about this, but basically, first of all, there's atomic operations. In MongoDB, there's no such thing as an atomic operation. So if you execute 10 things at a time, some of them may fail or the rest not, and the application will be left in an intermediate state. This is extracted from the documentation, so basically there's no way for doing that in MongoDB. There's neither clean reads. By clean reads, I mean a read which is consistent to a given view of the database. If you start doing a query in MongoDB, you may find yourself basically reading the same document twice. Or as a recent post made to the headlines a couple of weeks ago, if you're reading documents with an index in MongoDB, the index, and this is documented, may not find all the entries there are in the database. This is because of the way internally it works. Well, surprise, in TourDB, first of all, there's atomic operations because we are running off transactions. And there's also clean reads because we're also running off transactions. In this case, we're reading in repeatable read mode, which warranties us that we are given a consistent state of the database when the query happens. And this, again, is quoting the MongoDB documentation. I'm not saying anything that they are not saying. However, how easy it was for us to implement basically these clean reads? It took us 2 lines of code, which are on the bottom of the slides. It just basically set the transaction isolation to repeatable read mode and the transaction to read only. 2 lines of Java code to accomplish this otherwise very important feature. Now, how do we do replication and sharding? Which is, of course, one of the most important topics for NoSQL. Let's start with replication. As of replication, we have also implemented the wire protocol that MongoDB uses for replication. So far, it only works as a secondary node. So we replicate from a MongoDB master or a MongoDB slave, for that matter, and copy all the data asynchronously live from the original node and replicate that information again into a database like PostgreSQL. So this is very useful for if you have a MongoDB cluster already running. You can just attach TourDB as a replica node, and it will replicate all the information, and then you have all your data in a relational database, and now you can use SQL for querying the same data that will get inserted into the regular cluster. This is very useful because there's many people who basically are using MongoDB, and then they have big problems when they trying to do data analysis. Because, again, it's not designed for this kind of workloads. You know, it's big data, but only for inserts. And so many people are doing ETL processes to transform this data into a relational form and then query data in a relational specialized database. Well, good news is that you don't need to do anything. Just connect TourDB as a secondary node, replicate all things, all data, and you'll have that on your relational database. What about sharding? Sharding, we haven't implemented yet the sharding part of the MongoDB protocol, but it's on our roadmap, so we will do that for the next TourDB version. However, we are providing, as of today, sharding via the backend. If rather than using PostgreSQL, you use one of the other databases that we also support, which the database itself, it's a sharded, a distributed database like GreenPlum, then you'll have the sharding at the backend level. So it will be the database doing the sharding. And that's how we can accomplish sharding in a very powerful way, as I'll show you later in a benchmark. So let's talk a little bit about the software. First of all, I already mentioned it. It's written in Java. Current version, which is 0.4, it requires Java 7. Next version is going to require Java 8. We try to basically keep the minimum level of Java compatibility, especially for enterprise environments, but you know, it's impossible nowadays, and it's a pain not to be able to use Java 8. So now you're happy you can do anything at the code level. It's been so far tested mainly with Oracle VM, a little bit with the IBM, JVM. We would like to also benchmark with ASL systems. So I believe this is really cool. Anyone from ASL here today? No? Okay, out of luck. The idea is that TourDB is distributed as a jar file. Right now it's distributed as a jar file, and a jar file with a typical shell script and .bat for Windows users wrappers. But we also want to distribute as an ER file, so you could deploy directly to your app server, and then your relational database now has NoSQL capabilities. So it should be very easy to deploy. One thing that is critical for us, because basically we're a startup in Spain, we're not a very large company, put it really hard for us to develop a database from scratch. So rather than doing that, we try to use as many well-known tested dependencies that we could use in our code, which are also open source. So we believe those are giants for us, and we are leveraging all the capabilities that they provide us. First and foremost, I would say Netty. How many of you here know or use Netty, the network I/O framework? Okay, a few of you. I believe it's a really great tool. It's an async framework for network I/O. It is really fast. It is kind of event type, which basically means that on a few threads does all the work in a completely asynchronous manner. It has its own memory management internal solution, and it's really fast. So it helps us a lot. All the Mongo protocol is implemented on top of Netty. We also use Juke, J-O-O-Q. Who uses Juke here? Or knows about Juke? Okay. Juke is an excellent tool for doing queries to the database. If you use an ORM, I would probably suggest you to look at Juke. I'm not a big fan of ORMs myself, especially since you don't have a lot of control over the SQL code which you can throw to the database. And one of my main points here is that if you use SQL, which is extremely powerful, you can do many powerful things. Well, Juke basically allows you to do that, but without working like in an ORM environment, but in such a way that it's also typed. So you're going to be writing SQL code or code in Java that looks extremely like SQL. It's typed, it's checked by the compiler, but it brings you all the power of SQL. So it's really good. Also use Hickory Connection Pooler, which is an amazing connection pooler. It's also really fast. It's provided a lot of speed in terms of pulling connections to the database, or referring to. Of course, Maven, Guava, and Juice. Who doesn't use Java, Guava, and Juice in their main projects? Well, many other tools, logback, findbacks, of course, the databases, Postgres, Greenplum, JDBC. We're going to talk a little bit about JDBC. What else? The code is very modular. We haven't run Sonograph over the code base yet to check whether we have any cyclic dependencies. Hopefully not. But good news is that if there is, this is open source, it's on GitHub, you can submit a pull request to fix it. We are very aggressive about modularity. And one of the reasons we think that is that we want those modules to be individually reusable. And many of them are, in fact. Like for instance, I'll mention it briefly, but we have one of those modules which is called MongoWP, Mongo Web Protocol. And that's a separate module, and it's a separate repository. And it's the implementation of the Mongo server protocol on top of Netty in Java. So if you would like to build a MongoDB server, even a mock one, you could rely on MongoWP. And at least theoretically, you don't even need to understand the protocol to be able to write a MongoDB server. So we try to make everything very modular. And some of the most important modules that we have is like, for example, D2R. D2R is document to relational. It is the secret sauce of what we're doing, right? How we transform from unstructured data to structured data to relational data. And that's a separate module. I don't know if you use it for anything, but it makes our life easier because it creates a wall of separation, divide and conquer. We also have Kiwi document. Kiwi document is the abstraction I was referring to before in terms of basically separating the representation of the unstructured data, the JSON data, from the meaning of it. So in the future, if you write an implementation of a different protocol that transforms from whatever protocol, let's say Couchbase, into Kiwi document, TourDB will also work with Couchbase. And this is, of course, on our roadmap. And of course, the database, the backends, which can be, are somehow pluggable right now. So even though we started with Postgres, we have now experimental implementations with both MySQL and Greenplum, and all the databases are on our roadmap too. What I mentioned, yeah? Question?
Since you mentioned databases, Your first slide, I'm going back to your first slide.
Okay.
Of the four requirements that we look for in the database, you missed one.
Go ahead.
And the one you missed was, I want a system admin to take ownership. At the enterprise I work for, we've got Unix sysadmins, we've got Windows sysadmins, and we've got one group who actually do a good job. And that's our Oracle DBAs. And what you said so far sounds really, really neat. But if I can't write to an Oracle database, fuck.
Okay, that's fair enough. And that's why, while we started this way, we wanted to have such abstractions that we could plug in different databases later on. Needless to say, the Oracle database is the current market leader, and it's something we will target.
But you haven't addressed it yet.
Not yet. Good news is that...
Because we've got people using MongoDB, and the only reason they're using MongoDB because excuse me, I'm cursing, too fucking lazy to write a schema.
Yeah?
And
That's just an opinion.
yes, that's just an opinion.
I mean, that's,
You may be using MongoDB for a good reason.
MongoDB is not for that. It's not true.
MongoDB.
We are talking about link stack. It's JSON.
There are valid reasons to use
Yeah,
MongoDB.
okay.
Let's let Alvaro finish.
So, well, I will agree with many of the statements issued here. What I can say is that people use MongoDB, right, for whatever reasons. And yes, we want to provide, for people who have relational databases like Oracle too, a way of providing those people MongoDB compatible layers so they can be as happy as they will be, right? Probably even more because there's clean reads and more durability and so on, but at least the same. And that's in our roadmap. If you're very specifically interested in one use case, such as this one, we can talk later. We accept projects as funding requests to develop new open source software, so we'll be happy to talk. Okay.
well, it sounds to me that the two things, which is reason and consequence, is completely reverted here.
Okay.
I mean, let's just look at the reality that what's happening before MongoDB and other NoSQLs came into being. Relational databases were there for a long time, and you know, thousands and tens and hundreds of thousands of you know, business analysts and developers and other operators and other people knew how to deal with them. So the reason why MongoDB and others, not just MongoDB, you know, came to existence is because relational databases could not cope with the amount of data that bigger companies already got accustomed to, and they could not use those relational databases. So all of this looks like very nice and neat student project, but I don't see any real, you know, value in all of this, because the value of NoSQL databases is just that they deal with the amounts of data where relational databases could not deal. So unless you're talking about terabytes or petabytes of data sets that NoSQL database can operate on and you know, can reliably get the data and query and stuff like that, this is not serious.
Okay, it is a very fair question. If just in case you haven't heard it, basically the summary is that NoSQL databases mainly came into place for being able to handle really large amounts of data. And what is it doing to handle those large amounts of data? Well, the answer might be a little, of course it is only my opinion, but might be a little bit surprising. NoSQL databases are terrible in managing large amounts of data, especially MongoDB. And one of the reasons why that happens is precisely because of how they store data. If you remember this picture that I've shown before, I'm not saying that all the NoSQL databases are bad or cannot store a large amount of data, but I've seen so many problems already with this that I've learned the hard way. Most NoSQL databases, definitely MongoDB, store information like this. So the more information you have, the more problems you'll have to query that information. Unless you only really want to store information, like for compliance, and you hopefully will never have to query it later, this is not okay, right? So I've had customers who every year they delete the old data and only serve 1 year window of data, because otherwise they cannot meet the query time requirements. So there's by the way, there was one blog post that MongoDB did some years ago. They deleted afterwards. That said how to scale your database beyond 100 gigabytes. There was like a 10 bullet point list. 100 gigabytes of data, right? That's nothing. So in reality, NoSQL databases are good for, it ended up being, the original idea was that one, I definitely agree with that. In my opinion, nowadays, NoSQL databases are used for schemaless, whether that's laziness or not, or flexibility. I don't want to get into that, but I would say schemaless, which by the way is a terrible term, let's say flexible schema, right? And high availability. Now, it's where they're definitely good at that.
It's not only that. The basic reason why NoSQL database exists is because they are distributed.
Okay.
If they are not distributed, then there is no much value into that. That's where relational databases cannot scale.
Yeah. Okay. So there's definitely some interesting reflection. I'll try to answer that quickly also to move on. But basically, so what NoSQL did was target a subset of what it's possible to represent in relational databases, basically skippable relations. And then it's very easy to distribute, because as long as data is isolated from each other, like in MongoDB as documents, one document is isolated to the other one, you can distribute, you can shard them. You can say, I'll store this one here and the other one there. Key value database, even more than that, right? Each key value is separated from the rest, so they can be stored anywhere. That's why it's easy to scale. In relational databases, data is related, so it's very difficult to find a general solution to the problem of distributing data. Now, the good news is that there's many relational databases that are distributed and are really good at that one. For instance, GreenPlum. GreenPlum is used on dozens of terabytes, hundreds of terabytes of databases. And if you design the schema in such a way that you will not have those kind of relations crossing partitions, performance is highly superior to most NoSQL databases.
Well, GreenPlum is running on specialized hardware.
Not need to.
Well,
and it's open source right now.
And in fact, I mean, they lost their customers to the point that they are absolutely at distinction level.
Yeah. Well, I'll show you some benchmark comparing MongoDB performance and TourDB performance running on GreenPlum on AWS, no specific hardware. You'll see the numbers, and we'll keep discussing that. Okay, so I mentioned about sharding. We're using sharding at the database level now with GreenPlum. We'll have sharding exactly the same way as MongoDB does. So we'll have the same feature parity with MongoDB and in the way to scale distributedly. So I was talking about modularity, the support for many databases, and MongoWP, which is the implementation of the Mongo protocol that you can also use. A little bit about the architecture. So there's, at the top level, there's the MongoWP protocol that I mentioned before, and also the replication implementation of the Mongo protocol, which allows us, as I mentioned, to replicate from a MongoDB replica set, right? Under that, there's this MongoDB MongoWP layer that I mentioned before, and the KV document, which it's the abstract representation of JSON documents. And this allows us to, in the future, speak all the protocols, couch-based, right? Then we have D2R, which I already mentioned, is the document to relational, is the layer that transforms hierarchical nested structures into the relational set of tables. And then we have the executor. the executor, which I'll show you some architecture diagrams later, is the software responsible for, of course, executing jobs in the relational database. And it's one of the most complex parts of the TourDB project. It also has a cache, which is needed to avoid lookups to the database to infer the structure of the documents. And this basically allows us to do queries to the database exactly to the only tables that we know the information will be. And this information is cached. Fortunately for us, all the DDL we do to the database is immutable in the sense that we never change DDL, we only add DDL, so that this cache is easy to implement, and it's very small, by the way. We have the backend common code to support multiple backends, and then the specific backends code. So it's fairly easy, although a little bit involved database. Talking a little bit more about the executor, it is a little bit complex because we can have many incoming connections in parallel from the MongoDB protocol, which may refer to different or the same sessions. The way MongoDB handles users and connections is a little bit special. So we had to set up a general queue first. By queue I mean a Java executor, service executor. And from this general queue, we infer which jobs are sent to the user's queue, which map basically to connections, but not necessarily. And also the system queue. The system queue is used for queuing DDL operations, basically, to create tables and to increment sequence numbers and so on. And of course, there are some dependencies here because some user tasks may depend on the creation of some tables. So it's a little bit involved how this all works, but it's basically, as of today now, based on queues. What about performance, which is one point I wanted to get at. Well, first of all, let's show an OLTP benchmark. Typical benchmark for NoSQL, YCSB, Yahoo Cloud Serving benchmark on medium-sized Amazon machine on the AWS. We're focusing here, I wanted to focus on inserts only, and there are some conditions that are basically close to production, which is basically we're using rate concern enabled, journaling enabled, and replication enabled. I'm saying this because most MongoDB benchmarks are run on setups that aren't realistic and provide higher numbers that you'll never get in production. If you basically don't turn on journaling, you don't acknowledge your rights, and you don't turn on replication, that would mean you're using one single node. It turns out that performance drops significantly if you don't use it. So, how do we compare against MongoDB in terms of insertion? Well, we're not as fast as MongoDB, but we're not that far away, especially taking into account all the transformations that we're doing to the documents, the way we're structuring data, pre-creating tables, and the fact that we are still on 0.4 version, right? Now, let's look a little bit about data analytics benchmark, which is one of the points, one of the main advantages of using TourDB. In this case, we took an Amazon dataset. It's a dataset made of all the reviews for all the Amazon products on the web. Someone scraped that. It's a very small dataset anyway. It's like a 65 gigabyte. But here we wanted to use a sharded database, a distributed database. We're talking about distribution. So we took here 4 shards, MongoDB, and compared it against TourDB running on Greenplum, and Greenplum running on 4 segments. A segment is a shard. So on the same hardware and same everything. So first of all, this is how the disk space looks like. Less is better, because you're using less disk space, which means also less I/O and more memory, more information cached in memory. Here we're using even MongoDB with compression enabled with the latest engine, WireTiger, and the difference is pretty significant. TourDB requires basically 20 to 30% of the same disk space to store the same data. And this is just because we're not repeating the meta information all the time. And we are laying the information on disk in such a way that when using, in this case, Greenplum's columnar compression, it is perfectly aligned, so it compresses better. Then performance. For measuring this performance, we came up with some queries. And the first thing that I also wanted to show you as application developers, mostly probably here, is which API looks easier for you to do. The one on the left and the one on the right. The one on the left is pure SQL, the one on the right is the MongoDB Query API language. This one is more or less easy. What about this one? Well, probably the left side is easier to understand, but there's some even gotchas on the right side. You can see that there's a allow this is true flag, which is required the MongoDB to run basically queries that return results larger than 16 megabytes. All right, so how does it look like in terms of performance? Looks more or less like this. This is query times in seconds, so less is better. I believe this case, an image is better than 1,000 words. So I'll just skip to the next slide. All right, last but not least, some of the tricks and tips and the lessons that we learned while developing TourDB that might be useful for you. First of all, we use extensively the visitor pattern. Taking into account that there's many things that we need to know related to values and types, which have slight variations. Like there's a Boolean type, a number type, date type, and if you need to do many operations for all of these types, that's a lot of boilerplate code, but especially a lot of errors that you may make, like for example, not implementing one of those, that using a visitor pattern will help you go through. So this is one of the reasons that we use it, because the compiler can help you if you basically set up all the visitor methods in an interface, and then you don't implement one of those in one of the visitors, then the compiler will let you know. So we avoid these problems by using this pattern. So this is one of the tips that I would say to you, that it's a very interesting pattern, and it's very helpful in situations where you may have like these variations of many elements doing many things at a time. Monitoring performance, it is something that was not our initial focus. It is becoming more and more our focus, of course. And we have played with both Oracle Mission Control and Java VisualVM. Basically, Mission Control, it's amazing. It's a really good tool, very detailed information, and it's very interesting. However, it doesn't work for us in this case. And the reason why is that it doesn't show you the numbers regarding the other operations, the I/O operations, for example, the native code. And there's nothing we can see there. So it is excellent for instrumenting the pure Java code, but not what happens outside. In our case, we have a database. And we understand it might be a black box for Java monitoring tool, but we need to understand how much time is spent there. And this is something we have not been able to accomplish with Mission Control. And it's also very coarse-grained. We need more finer detail. The other option is Java VisualVM. And it is very fine-grained, and it gives us all the information that we need. So basically, this is a tool that we use for most monitoring the performance. Now, the problem is that the impact on performance it has, it's very significant. You can configure it more or less, but it's still very significant. And what it's worse is that it seems to be unbalanced. Some methods are more impact than others, and then the relative comparisons are bad for us. So there's no great tool right now for doing all of that at once. We're experimenting now with ProxyBuilder to create proxies of the classes which we want to instrument to gather information in real time about those. Then using HDR histogram, which is another great framework for finding out latencies, which is one of our main concerns, to be able to find all these answers. But it's not no easy task, definitely. What else? Documents and keys. So to put this briefly, one of the problems that we also experimented and found out while monitoring the performance is that we saw many times spent on hash maps. Indeed, looking in hash maps. It's like, first reaction is like, what? Right? After all, what it happens is that in a NoSQL database, there's a lot of keys and values. Most of the values at the end of the day are strings, and keys are definitely strings. So those all end up being in a hash map at some point, especially the keys. And looking at keys in large hash maps can become expensive because it involves equals on the strings, the keys, and equals is a method that if the object is the same, because the reference points to the same place, the operation is O1, However, if it's the same object with, different objects, even though they have the same value, they have the same string, the operation is on. And this on ended up being really expensive for us. So we had to create string pools. We tried, of course, the intern method in JDK and the Guava interning method. We ended up creating basically our own string pool because it was performing better. But it was a huge problem. It also created a lot of JSON pressure. And we tried to avoid all that with this basically pool of strings, which was necessary because many of the keys are, again, repeated throughout the execution of the database. We also had to deal with memory pressure because the clients are basically async to us. And so if we're slower than the clients are producing information to store in the database, which can happen, especially during an import process, well, we need to slow them down. And this is not easy, and especially we were seeing a lot of out-of-memory errors. The way we dealt with them, it's not perfect yet, but basically we are doing back pressure first of all, and also we are monitoring the use of memory in real time and stopping the clients at the netkey thread whenever there's high memory pressure. It's not ideal. We should do more back pressure in basically going down to the NATI level and the TCP level, but that will go sometimes. Some lessons learned. Some of the performance problems that we saw are non-obvious. So we saw some performance problems at some point, and it resulted that some code was being executed twice rather than one. It was idempotent, so it wasn't creating any problem, but it was a performance problem. And it's not obvious until you really got the deep metrics on that. So just to finish this talk, again, this is open source, so feel free to download, to clone the source code. It's on GitHub. Please, if you like this, go and give us a star on GitHub. And of course, more specifically, send pull requests to check the code, and if you can do any improvement, you like it, just do a pull request. We are very happy to accept those. Check out our frequently asked questions on GitHub. It's I would say fairly detailed, so you'll find a lot of information there. And we're looking for new developers, so if you want to contribute code, we would be very happy to have you on board. Thank you.